Hello, in this lecture we will study phasors for steady-state analysis. After studying the phasor notation, we will learn the phasors for R, L, and C elements. Then we will learn an important concept, the impedance, which is a frequency-dependent resistance, and also a related concept to that, the admittance. And at the end, we will conclude this lecture by writing Kirchhoff's laws using phasors. A sinusoidal current or voltage at a given frequency is characterized by its amplitude and phase angle. For instance, the current response of an RL circuit can be defined in the form IT is equal to real part of Im times e to the j omega t plus phi minus beta, or this real part due to the Euler's relation will correspond to Im times cosine omega t plus phi minus beta, where Im is the magnitude and phi minus beta is the phase angle and omega is the radiant frequency. We can rewrite the first equation here by separating the e to the j omega t term from the e to the j phi minus beta term. Remember, in the previous lecture, for the forced response for sinusoidal inputs at steady-state analysis, we have realized that all the terms in the equation was multiplied by e to the j omega t. Therefore, for finding the steady-state response, we can represent information using phasors by omitting the frequency information in the following form given here. I, the phasor, is equal to Im times e to the j phi minus beta, and similarly I can write this as a magnitude Im and phase phi minus beta as well. A phasor is a complex number that represents the magnitude and phase of a sinusoid. We are using here the term phasor for a vector because phasor is time-based rather than space, and when you sell phasors, you know that you are dealing with electrical circuits at steady-state analysis. A phasor, a complex quantity, can be represented in exponential, polar, or rectangular forms. And phasors for circuit analysis can be used if the circuit is linear, if we are doing steady-state analysis for a sinusoidal source, and all independent sources are sinusoidals and have the same frequency. Now we have some simple exercises. I have a current given by IT is equal to 5 times sine 100t plus 120 degrees. I always convert it firstly to cosine. IT is equal to 5 times cosine 100t plus 30 degrees. And writing it as a phasor is simply omitting the frequency term and writing the amplitude and phase or angle separately. Here I is equal to 5 times the angle 30 degrees. And similarly I can do the inverse. Here I have a phasor V is equal to 24 times angle 125 degrees, and I can write this in the time domain as Vt is equal to 24 times cosine, now omega t plus 125, because I don't know what the frequency of that phasor is. That information is omitted in the phasor notation. Therefore, here I need to just write omega and find the frequency information from somewhere else. Here we show step by step how to transform a signal or function from time domain to frequency domain, but practically the only thing you need to do in order to change it to a phasor notation is take the amplitude and the phase and write it in the exponential or this angular notation. Similarly, we can do the transformation from frequency domain to the time domain for a phasor given as y is equal to ym times e to the j beta, and here I end up with the amplitude and phase with a cosine function. However, the only thing which I don't know is the omega, because the radiant frequency information is not provided in the phasor notation. Find the steady state current when the voltage source is Vs is equal to Vm times cosine 100t and R is equal to 200 ohms and L is equal to 2 henries. So I will start solving this question by writing the KVL around this loop. L di over dt plus R times I is equal to Vs. And Vs is here Vm times cosine 100t, a sinusoidal function, and I can write this as the real part of Vm times e to the j 100t. And accordingly, I can write my solution I for the current as real part of some type of current magnitude times e to the j 100t plus beta. And now in order to find I and beta, I need to plug in this expression to this equation. And I can write j 100 times L plus R times I e to the j 100t plus beta is equal to Vm times ej 100t. And I can define my phasors I will write here a P such that it denotes the phasor, is equal to I times e to the j beta, and phasor V is equal to Vm times e to the j 0. And if I write these above equations again, I end up with j 100 L plus R times the phasor IP is equal to Vp, and from here I calculate IP as simply Vp over j 100 L plus R, and this is equal to Vp divided by j 200 plus 200, and I can write this further as Vp, which is Vm times 0 degrees, is equal to 283 times 45 degrees, and accordingly I can convert this back to a current in the form of I of t is equal to Vm over 283 times cosine, my frequency is 100t minus, because here it's at the bottom part, minus 45 degrees. So using phasors, I solved this steady state current question rather easily. Let us have a look at the phasor relationship for resistors. Ohm's law gives us the relation between the current and voltage for a resistor in the form of V is equal to R times I. At the steady state, we will have a voltage in the form of V is equal to Vm times cosine omega t plus Phi, and I can write this as the real part of Vm times e to the j omega t plus Phi. And similarly, the current will have a similar form as well. If I take 2 and 3 and plug into equation 1 in the phasor notation, basically by suppressing e to the j omega t terms, I end up with Vm times ej phi is equal to R times Im times e to the j beta. So for these two quantities to be equal, the left side and right side, we need to have phi is equal to beta. Therefore, I can write the phasor relationship in the form of V is equal to R times I. So in other words, the current and the voltage for a resistor element have the same phase. And now let us look at the phasor relationship for inductors. The constituent relationship for an inductor is given by V is equal to L times di over dt. And if we assume that the voltage V is in the form of Vm times cosine omega t plus Phi, which is the real part of Vm times e to the j omega t plus Phi, And if we assume that the current will have a similar form with a different phase and amplitude, by substituting 2 and 3 into equation 1, I end up with these expressions. The left side is a phasor for the voltage, Vm times e to the j phi, and right side, I take the derivative of the phasor for the current and multiply it with L. So I end up with this expression where I have j omega L times Im times e to the j omega b. Here we can write Im times e to the j omega b as the phasor I. Therefore, the phasor V is equal to j times omega L times I. So basically, we have a complex relationship between the voltage phasor and the current phasor, and also we multiply the current with the frequency. So for different frequencies, we will have different type of behaviors. And now the same for the capacitors. The constituent relationship for a capacitor is given by I is equal to C times dV over dt. And if we do the same analysis with a steady state voltage and current, I end up with I is equal to j omega c times V. So in other words, again, the relationship between the current and voltage depends on the frequency. And the current leads the voltage by 90 degrees because of the multiplication with j, because j is equal to e to the j times 90 degrees. And in this slide, we are summarizing the time domain and frequency domain representations of common circuit elements such as current sources, voltage sources, resistors, and capacitors. And we continue in this slide with inductors, current controlled voltage sources, and operational amplifiers. Basically, wherever you see a voltage, you just need to write the phasor of that voltage. And wherever you see a current, you need to write the phasor for that current. And if we have some type of differential relationship, you need to take the derivative of that constituent relationship, and then you just end up with terms similar to phasor V is equal to j omega L times phasor I for inductors, for instance. The current through an element is I is equal to 5 times cosine 103 amperes. Find the steady state voltage across the element for a resistor with R is equal to 10 ohms, an inductor with L is equal to 10 millihenries, and a capacitor with C is equal to 1 millifarads. Now the first thing I will do is I will write the current I in phasor notation, which will be 5 times the amplitude and with the angle of 0 degrees. And afterwards I will write the constituent phasor relationships for V, which is equal to V is equal to R times I for the resistor. V is equal to 1 over J omega C times I for a capacitor in the frequency domain, and V is equal to j omega L times I for an inductor. And I will simply plug in the phasor for the current into these equations and find the output voltages in phasor notation, and later convert these to the time domain. R is equal to 10 ohms, so then I will simply have 10 times 5 times the angle 0 degrees, and this will be 50 times 0 degrees. And accordingly, V of t for the resistor will be 50 times cosine 100t. Let's have a look at this. Here I have 1 over j times 100 times 1 millifarad, and this will be times I, and this will be equal to minus j. 1 over j is equal to minus j, and 1 over 0.1, so it will be 10 times 5 times 0 degrees, and this will be minus j times 50 times 0 degrees. but minus j is 90 degrees, so equal minus 90 degrees, so I will have 50 times minus 90 degrees for the V phasor, and accordingly V of t will be equal to 50 times cosine 100t minus 90 degrees. So this is the second one. Now let's do the third one with a different color such that we don't get confused. And here I will have j omega L. J times omega is 100 and L is 10 millihenry times 5 with the phase of 0 degrees. This will be equal to 5j 0 degrees. J is 90 degrees. Accordingly, this will be 5 times 90 degrees, and accordingly I can write V of t for the L element as 5 times cosine 100t plus 90 degrees, and this way I conclude the solution of this problem. Now we will cover an important concept called impedance, which is the ratio of the phasor voltage to the phasor current. Impedance is denoted by Z, and Z is equal to phasor V divided by phasor I. So in other words, this is the version of Ohm's law in phasor notation. So if the phasor V is equal to Vm times the phase phi, and the current I phasor is equal to Im times angle B beta, we have Z as equal to Vm over Im, and with the angle phi minus B beta. Impedance magnitude is Vm over Im, and the phase angle is phi minus beta. Impedance in AC circuits is similar or equivalent to the resistance in DC circuits. Because the impedance is the ratio of volts to amperes, it has the units of ohms. So, why is impedance useful? Impedance is the ratio of two phasors, but it is not a phasor itself. It's a complex number which relates voltage phasor to the current phasor, and phasors can be transformed to the time domain. However, we cannot do the same for the impedance. However, using impedances, we can solve the behavior of sinusoidally excited circuits using complex algebra rather than working with differential equations. As any other complex numbers, phasors and impedances can be written in several forms, which are the polar form, exponential form, and rectangular form. Since the impedance is a complex quantity, it consists of a real and imaginary part, and in electrical circuits, the real part is the resistance, and the imaginary part is the reactance. Both resistance and reactance are measured in ohms, and the magnitude of the impedance is equal to Z is equal to square root of R squared plus X squared, and the phase angle of the impedance, as we can see from this real imaginary Cartesian plane, theta is equal to arctangent X over R. Now, as an exercise, we will find the magnitude and phase of the impedance. Z is equal to 3 plus J 3 times square root of 3. The magnitude Z will be equal to square root of 3 squared plus 3 square root of 3 squared, and this will be square root of 36, and accordingly the magnitude is equal to 6. And angle theta will be equal to arctangent 3 square root of 3 divided by 3, and accordingly this will be arctangent square root of 3, and this is in degrees 60 degrees. So basically we found the magnitude and phase of this impedance. The impedance of a resistor is equal to R. The impedance of an inductor is Z is equal to J omega L. And similarly, the impedance of a capacitance is minus J over omega C. The reciprocal of impedance is called admittance and is denoted by Y is equal to 1 over Z. Admittance is also a complex quantity. Admittance is similar to the conductance for resistive circuits, and the units of admittance is Siemens, as it was the units of conductance for resistive circuits. In general, Y is equal to 1 over R plus Jx. We can write this as R minus Jx divided by R squared plus X squared, and this can also be written as G plus Jb. G here is called conductance and B is called as susceptance. So the impedance of an element can be represented in the rectangular form as Z is equal to R plus Jx. We call that an element is an inductive load if the reactive part X is positive, and we call that an element is capacitive if the reactive part X is negative. Because here, when we just look at the impedance of the inductor, we have positive J omega L. And for a capacitance, we have negative J over omega C. Now we need to find the impedance and admittance of the capacitor C is equal to 1 millifarad at omega is equal to 100 radians per second. Okay, Z is equal to 1 over J omega C, and this is equal to minus J over 100 times 0.001 millifarads, and accordingly this is equal to minus J10. And I can just also write this as Z is equal to 10 times minus J is minus 90 degrees is 10 times angle minus 90 degrees. And in order to find the admittance, I write Y is equal to J omega C, and this is equal to J times 100 times 0.001, and this is equal to J times 0.1. And from here I get Y is equal to 0.1 times 90 degrees. As you can see, Z is 10, Y is 1 over 10, 0.1 is the magnitude. 2.4 J. So here I created the frequency domain representation of the circuit using impedances and also phasors. Now I can use these elements in order to do circuit analysis. We have covered Kirchhoff's current law and voltage law previously for the time domain. KVL requires the sum of all the voltages around a loop to be equal to 0. And we can write 1, the equation 1, for the cosine waveform voltages as well, and their sum should be equal to 0 as well. And we can write this rule for the real part of complex exponential terms. And we can write these terms as phasors, and at the end, noting that e to the j omega t cannot be 0, the sum of phasors for a specific frequency around the loop should be equal to 0 as well. So in other words, Kirchhoff's voltage law holds in the frequency domain using phasor voltages. And we can also show that this is holding true for Kirchhoff's current law as well. So in other words, we can use basic KCL and KVL for circuit analysis using phasors as well. Similar to the resistances, we can state that the impedances in series can be summed as Z equivalent is equal to Z1 plus Z2 plus Zn. And similar to the resistances, we can state that the admittances in parallel can be summed accordingly. Y equivalent is equal to Y1 plus Y2 plus Yn. We also have the voltage and current division rules in the frequency domain using phasors. For instance, if we have two loads Z1 and Z2 in series with a voltage supply, we can say that V1 is equal to Z1 divided by Z1 plus Z2 times V, and V2 is equal to Z2 divided by Z1 plus Z2 times V. And the current division rule also applies. Parallel loads to a voltage or current source have the same voltage, and accordingly I1 is equal to Z2 divided by Z1 plus Z2 times I, and I2 is equal to Z1 divided by Z1 plus Z2 times I. So basically the same as resistances. We will use these rules in order to analyze circuits using phasors. So now we need to determine the steady state current IT in the RLC circuit using phasors and impedances. Please remember, if you would have not used phasors and impedances, we would have solved this question using second order differential equations, and it would not be easy. So therefore we are using phasors and impedances today by transforming the circuit to the frequency domain. Accordingly, this Vs will be equal to 100 times 0 degrees. The resistor is the same resistor. Z2 will be equal to minus J over omega C, and this will be equal to omega is 100 and C is 1 millifarad, so minus J 10, and Z3 will be equal to J omega L, which is equal to J times 100 times 0.01, and this will be J. So what should I do next? I should write Vs, the phasor, is equal to Z1 plus Z2 plus Z3, the impedances, the combined equivalent series impedance, times the phasor I, which I want to solve. So I will find I is equal to Vs divided by Z1 plus Z2 plus Z3, and this is equal to 100 as magnitude with 0 degrees divided by 9 plus minus J10 plus J minus J9, and this is equal to 100, the angle of 9 square root of 2 times minus 45 degrees, which is equal to 100 divided by 1272 times 45 degrees, and this is equal to, I is equal to, according to MATLAB, 7.86 times 45 degrees. Now I need to convert this back to the time domain, which is simply IT is equal to 7.86 times cosine. The phase is, the frequency is 100 T plus 45 degrees amperes. So using phasors, I could calculate the current very quickly. Now I have an RL circuit with the input to the circuit is the voltage source with Vs is equal to 7.28 times cosine 4t plus 77 degrees. And I have a 3 ohm resistor here and 0.54 Henry inductor. And I need to find the voltage over the inductor as the output voltage. So the first thing I will do is that I will convert this circuit to the frequency domain by writing the input voltage as a phasor, 7.28 with an angle of 77 degrees. And I need to be careful because this here is minus plus, so this will be a minus voltage. So then I can just kind of like convert the 3 ohms to a impedance, which is 3 ohms. And I can similarly create the impedance for this 0.54 Henry. So that will be J times 4 times 0.54, and this will be equal to J times 2.16. Then the phasor for the V out simply will be J 2.16 divided by 3 plus J 2.16 times minus 7.28 times 77 degrees the angle, and accordingly I will first get rid of this minus sign here, so I will have J 2.16, or I can just also write this as 2.16 times 90 degrees for J. And for the bottom part, I will need to do some calculations. So the magnitude will be 3.7, and the phase will be, according to MATLAB, 36 degrees. Times, I will convert this minus 7.28 to plus 7.28, and I will subtract 180 degrees. I could have either subtracted or added 180 degrees. So I will subtract, and I have 103 degrees here. And accordingly, V out will be equal to, I will write the magnitudes to this side, 2.16 times 7.28 divided by 3.7 times 90 minus 103, and also minus 36 degrees because it's at the bottom side, and according to this will be equal to, V out is equal to 4.25 times minus 49 degrees. And if I were to convert this to time domain, I end up with, since omega is equal to 4.25 times cosine 40 minus 49 degrees. And I can just also subtract 49 from 360 and write this as 4.25 times cosine 40 plus 311 degrees. Both of them are the correct answer. Alright, now I have a circuit consisting of resistors and a capacitor, and the input to the circuit is Vs equal to 8.93 times cosine 2t plus 54 degrees, so it is a sinusoidal input. And the corresponding output at the steady state is VOT is equal to 3.83 times cosine 2t plus 83 degrees. Now I need to find first this voltage VA with the plus polarity defined here and negative polarity defined here, and afterwards I need to find the value of the capacitor. If I were to convert the circuit to the frequency domain, I have here minus J times 1 over 2C, and I also have the phasors V0 and Vs. Let's start by finding V0 and Vs in the frequency domain. The phasor for Vs is equal to 8.93 with an angle of 54 degrees. And now it will be helpful for me to find the rectangular form of this. 8.93 times cosine 54 plus degrees here, plus j times 8.93 times sine 54 degrees, and accordingly Vs in this format will be equal to 5.25 plus j 7.22 if I did not make a mistake. And similarly V out will be 3.83 with 83 degrees, and again this will be equal to, in the rectangular format, 3.83 times cosine 83 degrees plus j times 3.83 times sine 83 degrees, and according to this will be equal to 0.47 V out, the phasor for V out, plus j times 3.8. So I have these two phasors. Now I can add or subtract them, and in order to find VA is equal to V out minus Vs, and accordingly I can find this easily. Is equal to VO is 0.47 plus J 3.8 minus 5.25 minus J 7.22, and this is equal to minus 4.78 minus J 3.42, and I can also write this in polar form as the magnitude of 5.88 and with an angle of 216 degrees. So I found the phasor for VA both in rectangular and polar forms. I have VA, V out, and Vs phasors, so I can right now write the KCL for node B, and that will be VA divided by 1 over J2C plus VA over 9 plus V out divided by 4 is equal to 0. And I can further simplify this as J2C times VA plus VA over 9 plus V0 over 4 is equal to 0. And I can further write this as J72C times VA plus 4VA plus 9V0 is equal to 0. And from here I can write C is equal to minus 4VA minus 9V out divided by 72 times J times VA. So now I need to calculate this expression to find the value of C. Alright, let us start our adventure in complex algebra to solve this question. C is equal to, I will make a long line here, minus 4 times VA. VA is given here, so it will be 19.12 plus 13.68J. Then I have minus 9V0. I will write it with different colors such that I don't get confused. V0 is given here, so I will have 4.23 minus 34.2J. And then for the bottom part, I will have 72 times J times VA. So J is whatever the angle of that VA, I will add 90, so the angle will be 306, and I will have 423 times an angle of 306 degrees. Let's write this upper part in a more convenient form. So 19.12 minus 4.23 is 14.89. Then I have 13.68 minus 32, 34.2, that is minus 20.52J. So I can also convert the upper part to the polar form, and then I will have 14 times 89 squared plus 20 times 52 squared, square root 25, 35, with an angle of minus 54 degrees divided by 423 and 306 degrees. This will be equal to, C is equal to 0.06 times minus 306 degrees, but minus 306 degrees is equal to 0 degrees, so it has only real part, and this is equal to 0.06 farads, and I can write this also as 60 millifarads. So basically I was able to solve this quite hard question using phasors and impedances rather quickly and easily. However, the phasor complex algebra for finding the impedances and phasors is quite cumbersome. So, but as long as we follow the rules and don't make any silly mistakes, we can solve the questions this way.